Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. When humanity first sets foot on Mars, the red dust beneath their boots will represent more than just an alien landscape. It will be the foundation of their survival. The dream of establishing permanent settlements on Mars hinges on a seemingly simple question. Can we grow food in Martian soil? The answer to this question will determine whether Mars becomes humanity's second home or remains forever a destination for brief scientific expeditions. Mars presents a formidable agricultural challenge. The planet's regolith, the loose layer of material covering solid bedrock, contains a complex mixture of minerals that would make any Earth farmer pause. Unlike the rich organic soils of our home planet, Martian soil lacks the fundamental building blocks of life as we know it. There are no earthworms tunneling through the substrate, no beneficial bacteria cycling nutrients, and no organic matter decomposing to feed future generations of plants. The composition of Martian soil tells a story of billions of years without life. NASA's Mars rovers, including Curiosity and Perseverance, have analyzed countless soil samples, revealing a regolith dominated by iron oxides, the source of Mars's distinctive red color. These iron compounds make up approximately 15 to 20% of the surface material, creating an environment that would be toxic to most Earth plants in concentrated amounts. Beyond iron oxides, Martian soil contains significant quantities of silicon dioxide, aluminum oxide, and calcium oxide. While these compounds exist in Earth soils, their proportions on Mars create unique challenges. The soil's pH levels range from mildly acidic to slightly alkaline, typically measuring between 6.5 and 8.5 on the pH scale. This range falls within acceptable parameters for many Earth crops, offering a glimmer of hope for agricultural adaptation. However, the presence of perchlorates presents the most significant obstacle to Martian agriculture. These chlorine-containing compounds, found in concentrations of 0.5% throughout Martian soil, are highly toxic to most Earth organisms. Perchlorates can disrupt thyroid function and pose serious health risks to humans and plants alike. The Phoenix lander first detected these compounds in 2008, fundamentally changing how scientists approach the possibility of life on Mars. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The temperature extremes on Mars add another layer of complexity to agricultural endeavors. Surface temperatures can plummet to -125 degrees Celsius during winter at the poles, while equatorial regions might reach a comparatively balmy 20 degrees Celsius during summer. These dramatic fluctuations would require sophisticated climate control systems for any agricultural operation. Water availability represents both a challenge and an opportunity. While liquid water cannot exist stably on Mars's surface due to low atmospheric pressure, subsurface ice deposits have been confirmed across much of the planet. The Mars Reconnaissance Orbiter has mapped extensive ice sheets just beneath the surface, particularly in mid-latitude regions. This frozen water could theoretically be extracted and processed for agricultural use, though the energy requirements would be substantial. The thin Martian atmosphere, composed of 96% carbon dioxide with only trace amounts of nitrogen and oxygen, cannot support plant life directly. Atmospheric pressure on Mars averages just 600 pascals, less than 1% of Earth's sea level pressure. This low pressure would cause water to boil at body temperature, making open-air agriculture impossible without pressurized environments. Despite these challenges, the dream of Martian agriculture continues to drive scientific innovation and research, setting the stage for humanity's greatest agricultural experiment. The robotic explorers that have traversed Mars over the past 2 decades have revolutionized our understanding of Martian soil composition, providing the foundational data necessary for future agricultural endeavors. These mechanical farmers, equipped with sophisticated analytical instruments, have painted a detailed picture of what awaits human colonists attempting to coax life from alien soil. The Mars Science Laboratory mission, better known as the Curiosity, rover has been analyzing Martian regolith since its arrival in 2012. Its sample analysis at Mars, or SAM instrument suite, has processed hundreds of soil samples, revealing a complex mineralogical landscape. The rover's laser-induced breakdown spectroscopy system can vaporize rock and soil samples from up to 7 meters away, analyzing the resulting plasma to determine elemental composition with remarkable precision. One of Curiosity's most significant discoveries involved the presence of water molecules chemically bound within Martian soil. When heated to approximately 800 degrees Celsius, Martian regolith releases water vapor equivalent to roughly 2% of the soil's total mass. This bound water represents a potential resource for future agricultural operations, though extracting it would require significant energy input and specialized equipment. The X-ray diffraction analysis performed by Curiosity revealed that Martian soil contains substantial amounts of olivine, a magnesium iron silicate mineral common in volcanic environments. This mineral, while present in some Earth soils, exists in much higher concentrations on Mars. Olivine weathers slowly in the presence of water, potentially releasing magnesium and iron ions that plants could utilize as nutrients. However, the weathering process also produces clay minerals that can affect soil structure and water retention properties. Plagioclase feldspar, another major component of Martian regolith, makes up approximately 20 to 30% of the soil in many regions. This aluminum silicate mineral contains calcium, sodium and potassium, elements essential for plant growth. The presence of plagioclase suggests that Martian soil might provide some necessary nutrients for plant development, though in different proportions than Earth plants have evolved to utilize. The Opportunity and Spirit rovers, which operated from 2004 to 2018 and 2010 respectively, provided additional insights into regional variations in Martian soil composition. Their findings revealed that soil chemistry varies significantly across different geographic regions, suggesting that future agricultural operations might need to be tailored to specific locations based on local regolith properties. Hematite, an iron oxide mineral, appears in varying concentrations across Mars's surface. While iron is essential for plant growth, excessive amounts can be toxic. The challenge lies in finding the optimal balance or developing techniques to modify iron availability in Martian soil. Some regions, particularly those identified by the Mars Global Surveyor's thermal emission spectrometer, show hematite concentrations that might require remediation before agricultural use. The detection of sulfate minerals throughout Martian regolith presents both opportunities and challenges. Sulfur is a crucial nutrient for plant protein synthesis, and its presence in Martian soil could support agricultural operations. However, high sulfate concentrations can create saline conditions that many plants cannot tolerate. The Mars exploration. Rovers discovered extensive sulfate deposits, particularly in areas that were once underwater, indicating ancient environmental conditions that might inform modern agricultural strategies. Pyroxene minerals detected by multiple rovers contain calcium, magnesium, and iron in silicate structures. These minerals weather more readily than olivine, potentially providing a more accessible source of plant nutrients. The abundance of pyroxene in certain Martian regions suggests that these areas might be more suitable for initial agricultural experiments. The granular structure of Martian regolith differs significantly from Earth soil. Electron microscopy images from various missions show angular, poorly sorted particles ranging from clay-sized fragments to small pebbles. This structure affects water retention, root penetration, and gas exchange, all critical factors for plant growth that will require careful consideration in agricultural system design. The discovery of perchlorates in Martian soil represents one of the most significant obstacles to establishing agriculture on the red planet. These chlorine-oxygen compounds, detected by multiple missions including the Phoenix Lander and Mars Science Laboratory, pose serious challenges that demand innovative solutions before any sustainable farming can occur on Mars. Perchlorates exist in concentrations averaging 0.5% by weight throughout Martian regolith, with some regions showing concentrations as high as 1%. To put this in perspective, perchlorates become toxic to most plants at concentrations as low as 0.01% in Earth soils. The ubiquitous presence of these compounds across Mars suggests they formed through global atmospheric processes over geological timescales. The formation mechanism of Martian perchlorates likely involves the interaction of chlorine-containing compounds in the atmosphere with ultraviolet radiation and electrical discharges. Mars's thin atmosphere provides little protection from solar UV radiation, creating conditions that favor the oxidation of chloride ions into perchlorate compounds. This process has been occurring for millions of years, building up the substantial concentrations observed today. Research conducted at the University of California, Riverside has demonstrated that perchlorate concentrations found in Martian soil samples would be lethal to beneficial soil microorganisms essential for plant growth. These microorganisms play crucial roles in nutrient cycling, nitrogen fixation, and disease suppression, functions that would be critical for establishing sustainable agriculture on Mars. Several promising remediation techniques have emerged, from terrestrial research on perchlorate contamination, biological treatment methods using specific bacteria capable of reducing perchlorates to harmless chloride ions show particular promise. Researchers at Stanford University have identified bacterial strains that can survive in Mars-like conditions while effectively degrading perchlorate compounds. These extremophile bacteria could potentially be introduced to Martian soil as a biological remediation system. Chemical reduction techniques offer another approach to perchlorate remediation. Iron-based reducing agents can convert perchlorates to chlorides under controlled conditions. Research teams at the Massachusetts Institute of Technology have developed zero-valent iron nanoparticles that can effectively treat perchlorate-contaminated soil. However, the energy requirements and resource needs for large-scale chemical treatment on Mars remain significant challenges. Electrochemical remediation presents a high-tech solution that could be powered by solar arrays or nuclear reactors. This process involves passing electrical current through contaminated soil, breaking down perchlorate molecules through electrochemical reactions. Laboratory experiments have shown 90% reduction in perchlorate concentrations using this method, though scaling up for Martian agriculture would require substantial infrastructure investment. Washing techniques, while simple in concept, could prove effective for initial soil preparation. Since perchlorates are highly water-soluble, repeated washing with water could remove significant concentrations. However, this approach would require large volumes of water, a precious resource on Mars, and would need to be combined with water, recovery and recycling systems to be practical. Recent experiments at Wageningen University have explored the potential for plant-based phytoremediation of perchlorate-contaminated soil. Certain plant species, including some varieties of willow and poplar trees, can absorb and concentrate perchlorates in their tissues without immediate mortality. While these plants couldn't be used for food production, they could serve as biological filters to gradually clean Martian soil over multiple growing seasons. The European Space Agency has funded research into combined remediation approaches that integrate multiple techniques. These hybrid systems might begin with chemical or electrochemical treatment to reduce perchlorate concentrations to manageable levels, followed by biological treatment to eliminate remaining traces. Such comprehensive approaches could make previously unusable Martian soil suitable for agricultural applications. Advanced soil processing facilities will likely be among the first major infrastructure projects on Mars. These installations would need to process large volumes of regolith continuously, removing perchlorates while preserving beneficial minerals and soil structure. The energy requirements for such operations would be substantial, necessitating reliable power generation systems capable of supporting continuous industrial operations in the harsh Martian environment. Scientists around the world are conducting groundbreaking experiments that bring us closer to understanding how crops might grow in actual Martian conditions. These experiments using carefully crafted Mars soil simulants, represent humanity's first steps toward becoming an interplanetary agricultural species. The results are both encouraging and sobering, revealing the immense challenges while demonstrating the remarkable adaptability of Earth life. The Mars Desert Research Station in Utah serves as one of the primary testing grounds for Mars analog agriculture. This facility, operated by the Mars Society, provides researchers with an environment that closely mimics the isolation and resource constraints that future Martian colonists will face. Here, teams of scientist-astronauts conduct extended experiments growing food crops using Mars soil simulants while living under strict resource limitations. Dr. Vega Varmelink at Wageningen University has conducted some of the most comprehensive Mars agriculture experiments to date. His team has successfully grown tomatoes, radishes, peas, and wheat in Mars soil simulant, achieving yields that could potentially support human nutrition needs. The experiments revealed that while plants can grow in Mars-like soil, they require careful nutrient supplementation and pH adjustment to achieve optimal growth rates. The Mars soil simulant used in these experiments, known as MGS-1, is based on volcanic soil from Hawaii that has been modified to match the mineral composition and particle size distribution of actual Martian regolith. This simulant contains the same problematic iron oxide concentrations and pH levels found on Mars, while safely excluding the toxic perchlorates that make direct experimentation with real Martian soil dangerous. One of the most significant findings from these experiments involves the role of earthworms in Mars soil conditioning. Wermelink's team discovered that introducing earthworms to Mars soil simulant dramatically improved plant growth and soil structure. The earthworms broke down organic matter, improved soil aeration, and created nutrient-rich castings that enhanced plant development. However, the question remains whether earthworms could survive the harsh conditions of Mars, even within protected greenhouse environments. NASA's Kennedy Space Center has developed its own Mars soil simulant, called JSC, Mars 1A, which more accurately represents the fine-grained nature of Martian dust. Experiments using this simulant have focused on hydroponic and aeroponic growing systems that might be more practical for Mars missions. These soilless growing methods eliminate many soil chemistry problems while conserving water and nutrients, critical considerations for resource-constrained Mars operations. The selection of appropriate crop varieties for Mars agriculture involves multiple criteria beyond simple growth capability. Plants must be nutritionally dense, space-efficient, fast-growing, and capable of thriving in controlled environments with artificial lighting. Potatoes have emerged as a leading candidate, offering high caloric density and complete amino acid profiles. The International Potato Center in Peru has collaborated with NASA to identify potato varieties that could grow in Mars-like conditions. Leafy greens, including lettuce, spinach, and kale, show particular promise for early Mars agriculture. These crops grow quickly, require relatively little space, and provide essential vitamins and minerals that would be difficult to obtain from processed foods during long-duration space missions. Experiments at the University of Arizona's Controlled Environment Agriculture Center have demonstrated successful growth of multiple leafy green varieties in Mars soil simulants. Legume crops, such as beans and peas, offer unique advantages for Mars agriculture through their ability to fix atmospheric nitrogen. However, Mars's atmosphere contains only 2.8% nitrogen, compared to Earth's 78%, making nitrogen fixation less efficient. Research teams are exploring whether genetically modified versions of nitrogen fixing bacteria could enhance legume performance in low nitrogen environments. The psychological benefits of fresh food production have become an unexpected focus of Mars analog experiments. Researchers at the Hawaii Space Exploration Analog and Simulation Mission, or HICs, have documented significant improvements in crew morale and mental health when fresh vegetables supplement preserved rations. These findings suggest that Mars agriculture will serve purposes beyond mere nutrition, contributing to the psychological well-being of isolated colonists. Recent experiments have explored the potential for perennial crops that could provide sustained harvests over multiple growing seasons. Fruit trees, while requiring more space and time to establish, could eventually provide high-value nutrition and psychological benefits. Dwarf fruit tree varieties, developed for terrestrial container growing, show promise for adaptation to Mars greenhouse environments. The future of Mars agriculture lies not in open fields under alien skies, but within sophisticated controlled environment agriculture systems that will serve as the lungs, kidneys, and digestive system of human settlements. These enclosed ecosystems must accomplish the seemingly impossible, creating Earth-like growing conditions within one of the most hostile environments in the solar system. The design of Martian greenhouses represents one of the most complex engineering challenges in human space exploration. These structures must maintain Earth-normal atmospheric pressure while protecting plants and humans from radiation, temperature extremes, and the near vacuum of Mars' atmosphere. The European Space Agency's MELISSA project, which stands for Micro-Ecological Life Support System Alternative, has developed prototype closed-loop systems that integrate plant growth with atmospheric processing and waste recycling. Atmospheric management within Martian greenhouses requires precise control of gas concentrations that Earth plants have never experienced. Mars' atmosphere, composed primarily of carbon dioxide, actually provides an advantage for photosynthesis, as plants can utilize the abundant CO2 directly. However, oxygen levels must be carefully maintained for both plant respiration and human safety. Advanced atmospheric processors will continuously monitor and adjust gas mixtures to optimize plant growth while ensuring human habitability. The challenge of atmospheric pressure control cannot be overstated. Earth plants have evolved under approximately 100,000 pascals of atmospheric pressure, while Mars provides less than 1,000 pascals. Maintaining Earth normal pressure requires robust structural engineering and reliable sealing systems. Any breach in the greenhouse envelope could be catastrophic, leading to explosive decompression that would instantly kill all plant life. Water recycling systems represent the circulatory system of Mars agriculture. Every drop of water used for irrigation must be recovered, purified, and reused in a closed-loop system. Advanced hydroponic and aeroponic systems can achieve water use efficiencies of over 95%, compared to traditional soil-based agriculture that typically loses 30 to 50% of applied water through evaporation and runoff. The University of Arizona's Biosafety Level Agriculture Facility has developed prototype water recycling systems that can process plant wastewater, human waste, and atmospheric moisture into clean irrigation water. These systems use a combination of physical filtration, biological treatment, and advanced oxidation processes to ensure water quality meets strict agricultural standards. The energy requirements for continuous water processing represent a significant portion of the total power budget for Mars agricultural operations. Lighting technology for Mars agriculture must overcome the challenge of reduced solar intensity and the need for year-round growing seasons. Mars receives only 43% of the solar energy that reaches Earth, and seasonal variations can reduce this further. Light-emitting diode, or LED, technology has revolutionized controlled environment agriculture by providing specific wavelengths optimized for plant photosynthesis while minimizing energy consumption. Research at the Netherlands Organization for Applied Scientific Research has developed LED systems that can support plant growth using 60% less energy than traditional high-pressure sodium lights. These systems can be fine-tuned to provide specific light spectra for different growth stages, potentially accelerating plant development and increasing yields in the limited growing space available on Mars. The integration of agriculture with life support systems creates synergistic benefits that make Mars settlements more sustainable. Plants naturally purify air by consuming carbon dioxide and producing oxygen, reducing the load on mechanical atmospheric processes. A typical Mars greenhouse producing food for 4 people could process approximately 12 kilograms of carbon dioxide daily while generating 9 kilograms of oxygen, a significant contribution to life support requirements. Waste heat from other settlement systems can be utilized to maintain optimal growing temperatures in Martian greenhouses. Nuclear reactors, fuel cells, and electronics generate substantial waste heat that would otherwise need to be dissipated. Clever thermal management systems can redirect this waste heat to agricultural areas, reducing the overall energy requirements for climate control. Advanced automation and artificial intelligence will be essential for managing the complexity of Mars agricultural systems. Sensor networks monitoring thousands of variables, from soil moisture and nutrient levels to atmospheric composition and plant health, will require sophisticated control algorithms to maintain optimal growing conditions. Machine learning systems could potentially optimize growing conditions based on continuous performance feedback, gradually improving yields and efficiency over time. The psychological aspects of agricultural spaces have led designers to consider aesthetic elements that might seem frivolous but prove essential for human mental health. Natural lighting cycles, the sound of flowing water, and the visual appeal of growing plants contribute to psychological well-being during long-duration isolation. These human factors may prove as critical to mission success as the technical performance of agricultural systems. The selection of crops for Mars represents one of the most critical decisions in planning human settlement of the red planet. Unlike Earth agriculture, where thousands of crop varieties provide dietary diversity and redundancy, Mars agriculture will initially depend on a carefully chosen portfolio of plants that must meet strict criteria for nutritional completeness, resource efficiency, and environmental adaptability. Nutritional requirements for Mars colonists differ significantly from typical Earth dietary recommendations. The physical and psychological stresses of living in an isolated, dangerous environment increase caloric needs, while making certain nutrients more critical for maintaining health. Research conducted during Antarctic expeditions and long-duration space missions has revealed that colonists require higher levels of certain vitamins and minerals to maintain optimal physical and mental performance. Potatoes emerge as perhaps the most promising staple crop for Mars, offering exceptional nutritional density and caloric yield per unit of growing space. A single potato plant can produce up to 2 kilograms of tubers, providing carbohydrates, complete proteins, vitamin C, potassium, and other essential nutrients. The International Potato Center has identified 14 potato varieties that show particular promise for space agriculture, including varieties that can tolerate the temperature fluctuations and artificial lighting conditions expected in Mars greenhouses. Sweet potatoes offer additional advantages over regular potatoes, including higher vitamin A content and the ability to grow in slightly more challenging soil conditions. NASA's research has shown that sweet potato vines can also serve as leafy vegetables, essentially providing 2 crops from a single plant. The orange-fleshed varieties developed in Africa for combating vitamin A deficiency could prove invaluable for Mars nutrition programs. Quinoa represents a revolutionary choice for Mars agriculture due to its exceptional nutritional profile and environmental adaptability. This Andean grain provides all essential amino acids, making it a complete protein source equivalent to meat or dairy products. Quinoa can tolerate extreme temperature variations, high salinity, and low water availability, conditions that closely match the challenges of Mars agriculture. Research teams in Bolivia and Peru are developing quinoa varieties specifically optimized for controlled environment growing systems. Leguminous crops, including soybeans, lentils, and chickpeas, serve dual purposes in Mars agriculture by providing high-quality protein while fixing atmospheric nitrogen through their relationship with rhizobia bacteria. However, the low nitrogen content of Mars' atmosphere may limit the effectiveness of biological nitrogen fixation. Genetic engineering research is exploring ways to enhance nitrogen fixation efficiency or modify plants to utilize alternative nitrogen sources available in processed Martian regolith. Leafy green vegetables will be essential for providing vitamins, minerals, and dietary fiber that cannot be obtained from staple crops alone. Lettuce, spinach, kale, and Swiss chard have all demonstrated successful growth in Mars soil simulants. These crops grow quickly, allowing for multiple harvests per year and require relatively little growing space compared to their nutritional A contribution. The psychological benefits of fresh, colorful vegetables may prove as important as their nutritional value for maintaining colonist morale. Tomatoes present both opportunities and challenges for Mars agriculture. While they provide essential nutrients including lycopene and vitamin C, tomatoes require more complex environmental controls and longer growing seasons than many other crops. Cherry tomato varieties show more promise than large fruited types due to their faster maturation and higher yield efficiency. Research at the University of Arizona has developed compact tomato varieties specifically designed for space agriculture applications. Genetic modification will likely play a crucial role in adapting Earth crops for Mars conditions. Scientists are exploring modifications that could help plants tolerate the unique stresses of Mars environments, including enhanced radiation resistance, improved water use efficiency, and the ability to utilize nutrients from processed Martian regolith. However, the complexity of genetic modifications means that extensively engineered crops may not be available for early Mars missions. The development of Mars-specific cultivars through traditional breeding techniques offers a more near-term approach to crop improvement. By selecting plants that perform well in Mars analog conditions and breeding them over multiple generations, researchers can develop varieties optimized for Mars agriculture without the regulatory and technical challenges associated with genetic modification. Seed storage and genetic diversity represent critical concerns for Mars crop selection. Unlike Earth agriculture, where genetic diversity is maintained through wild relatives and extensive seed banks, Mars agriculture will depend entirely on the genetic material transported from Earth. Maintaining genetic diversity within limited space and mass budgets requires careful planning and possibly advanced techniques, such as cryogenic seed storage or tissue culture preservation systems. The transformation of Mars from a barren wasteland to a world capable of supporting human civilization will unfold through an agricultural revolution unlike anything in human history. This revolution will not happen overnight, but will evolve through distinct phases, each building upon the successes and lessons learned from previous stages, ultimately creating a new branch of human civilization rooted in Martian soil. The first phase of Mars agriculture will focus on survival-level food production for small research outposts. These initial facilities, supporting perhaps a dozen researchers, will rely heavily on Earth-supplied resources and highly controlled, growing environments. Success at this stage will be measured not in tons of produce, but in the percentage of dietary needs met by locally grown food. Even achieving 20 to 30% food self-sufficiency would represent a revolutionary breakthrough in space exploration. Advanced biotechnology will accelerate the development of Mars-adapted crops far beyond what traditional breeding could accomplish. CRISPR gene editing technology, already being used to develop drought-resistant and nutrient-enhanced crops on Earth, will be adapted for Mars-specific challenges. Scientists envision crops engineered to thrive in low-pressure environments, utilize perchlorate-contaminated soil, and even incorporate radiation-resistant genes borrowed from extremophile organisms discovered in Earth's most hostile environments. The scaling of Mars agriculture from research stations to permanent settlements will require revolutionary advances in automation and robotics. Agricultural robots capable of planting, tending, harvesting, and processing crops will be essential. As settlements grow beyond the capacity of human labor alone, these systems must operate reliably in Mars' harsh environment, while requiring minimal maintenance and repair capabilities that can be provided locally rather than depending on Earth-supplied components. Vertical farming technology will reach new heights of sophistication on Mars, where every cubic meter of pressurized space represents a massive investment in infrastructure and energy. Multi-story growing facilities could produce food equivalent to traditional farms covering hundreds of acres on Earth. Research at Singapore's vertical farming facilities suggests that yields per unit area could be increased by factors of 10 to 50 compared to traditional agriculture, making intensive food production viable even within the space constraints of early Mars settlements. The economic implications of Mars agriculture extend far beyond simple food production. Successfully growing food on Mars will reduce the cost of human presence on the planet by orders of magnitude. Current estimates suggest that transporting food from Earth to Mars costs approximately $10,000 per kilogram. Achieving food self-sufficiency could make the difference between Mars remaining a destination for brief scientific missions and becoming a permanent human settlement. Closed-loop ecological systems will evolve from simple greenhouse operations to complex ecosystems that integrate multiple species in symbiotic relationships. These systems might include not only food crops, but also trees for oxygen production and psychological benefits, beneficial insects for pollination, and even small animals that could provide protein while contributing to nutrient cycling. The development of such complex ecosystems represents a step toward partial terraforming of enclosed spaces. The long-term vision of Mars agriculture includes the gradual expansion of growing areas outside of fully enclosed facilities. As atmospheric processing technology advances and local conditions improve, partially protected growing areas could expand the scale of food production beyond what enclosed facilities can support. This transition might begin with hardy crops grown under simple plastic shelters and gradually progress to more complex agricultural systems as local environmental conditions improve. Soil development on Mars will transform from a technical challenge to a biological process as agricultural systems mature. The introduction of Earth microorganisms, carefully selected and possibly genetically modified for Mars conditions, could begin the slow process of creating living soil from sterile regolith. This biological soil development could take decades or centuries, but would ultimately create the foundation for a truly self-sustaining Mars biosphere. The psychological and cultural impacts of successful Mars agriculture cannot be understated. The ability to grow fresh food will transform Mars from a hostile frontier outpost to a place that feels like home. Seasonal harvests, the aroma of fresh bread made from Mars-grown grain, and the simple pleasure of eating a tomato grown in alien soil will mark the transition from survival to civilization. The success of Mars agriculture will ultimately determine whether humanity becomes a truly spacefaring species. The techniques developed for growing food on Mars will be applicable to lunar bases, asteroid mining operations, and generation ships. Traveling to other star systems, Mars agriculture represents not just the key to settling the red planet, but the foundation for human expansion throughout the solar system and beyond, marking the beginning of humanity's transformation from a single-planet species to a civilization that spans the cosmos.